Hello everyone. My name is Cass from University of Sheffield. Very happy to present our work today, a comparative study of using pre-trained language models for toxic comments classification. Recent years, many pre-trained language models have been introduced for text classification tasks. The basic idea is to first train a language model on a huge corpus, and then use the pre-trained language model on a downstream text classification tasks. We can also think the training process into two stages, the pre-training stage and the classification training stage, which is the downstream task training stage. Many research have proved the powerful performance of pre-trained language models. Popular models include BERT, RoBERTa, XLM, etc. Also, many methods have been proposed to further improve the performance of pre-trained language models on the downstream text classification tasks. For example, using complex downstream architectures, or continue the pre-training the language model and then transfer it to the downstream tasks. Particularly, there is one pre-training in domain method called the TAPT, short for Task Adaptive Pre-training. In this paper, the authors create an unlabeled training corpus from the target task by just getting rid of those labels. So the model is continued pre-trained on unsupervised learning style first, and then transfer the pre-trained twice language model to the target tasks. Having said that, in short, there are many studies using pre-trained language models on text classification, and we do have lots of options here for those models and for how to use those models. However, there are very limited works have been done on using pre-trained language models on toxic comments classification tasks. Especially, it's still unclear how to best make use of pre-trained language models for tasks like toxic comments classification. We will use TCC for short for toxic comments classification for the rest of the presentation. So, therefore, we specify the questions from three perspectives. First, how do different pre-trained language models perform on different downstream TCC tasks? Second, how do different downstream neural network structures impact on the performance of those TCC tasks? Third, can we use continued pre-training in domain to improve the performance on downstream TCC tasks? And if so, can we further improve the efficiency of the training process while maintaining the performance? Here we are talking about using less computation resources. So to answer the questions, we have studied the impact of downstream neural network architectures and continue the pre-training of language models with a further exploration of lightweight training parameters. We also studied the performance differences between pre-trained language models recently. So our study includes two parts. The first part, we analyze the impact of complexity of the downstream network architectures. We tested three different downstream architectures and three different pre-trained language models. So in total, we have 9 models for this part, and we also evaluate models on 4 different datasets. In the second part, we explore the performance of continued pre-training in domain using minimum computing resources, which we refer to as TAPT Lite. We reduced the batch size from 2048 to 16. We also experiment with different approach values to further reduce the computing resources requirement. The original TAPT used 100 approach, but we tried different approach values in our experiment. So in the first part, we analyze the impacts of complexity of the downstream network architecture. We compare 3 different downstream networks, namely a simple linear classification layer. The second one is CNN plus a linear layer. The third one is LSTM plus a linear layer. We have tested the 3 downstream architectures on BERT, RoBERTa, and XLM separately. So therefore we have 9 models in total to examine the different downstream architecture. Here is an example of BERT. So the BERT with a linear layer on top is our baseline model. And model 1 uses CNN plus linear. Model 2 is use LSTM plus linear. Actually, RoBERTa and XLM are tested in a similar way. So in part 2, we experiment with the TAPT Lite. As introduced before, the training process of TAPT includes 2 stages. So first, continue the pre-training the model using unlabeled data from the target task, and then train the model supervisedly with labeled target task. We have experiments with much lower parameter settings, where the batch size is only 16 compared to 2048 in the original paper. We also tried a different approach from 1 to 100. Let's see the results. So in the first study, this table shows the results from the first part. As mentioned before, we have 9 models in total to test the 3 different downstream architectures and 3 pre-trained language models. As we can see here, the micro F1 results indicates that the baseline model consistently perform much better than their complex counterparts, where CNN and LSTM is used as a downstream network architecture. In terms of micro F1, the baseline models obtain the highest F1 across all datasets, with the exception of XLM on the Fountain dataset. The biggest difference compared to CNN and LSTM downstream network architectures are on the smaller datasets like these 3. So the results here suggest that transferring a pre-trained language model to complex downstream network architectures does not offer any benefits over a simple linear structure in the context of TCC tasks. Now we come to the second part of our study. So in the second part, we also have tried 3 different pre-trained language models. And due to we use the different parameters here, we have 21 models in total. So here are the results. Firstly, if we look at the overall results, we can find that continued pre-training on the target task often leads to better performance compared to the baseline model. Particularly on the smaller datasets, the performance improvements are noticeable when using TAPT Lite. The higher increase of micro F1 compared to the micro F1 also tell us that the continued pre-training particularly benefits small classes in the dataset. And these are often the classes of toxic comments rather than non-toxic comments. Another finding is that there is no consistent pattern in terms of which approach setting is the best across 4 tasks. However, for multi-class classification tasks, which is these three. Continue the pre-training for 10 or 20 airports achieve the highest F1 scores or comparable results to their counterparts that use a higher approach value. For the multi-label classification task, continue the pre-training in domain does not show noticeable benefits on it. This may be related to the size of dataset. This dataset is more than 3 times bigger than other three, and the baseline model have learned, maybe the baseline model have learned enough from the dataset. While model-wise speaking, TAPT Lite benefits RoBERTa more than BERT and XLM when comparing their best TAPT Lite models. Also, if you compare the best TAPT Lite model and the baseline model on each TCC tasks regarding their micro F1. Well, TAPT Lite benefits XLM more than RoBERTa and BERT when particularly on TCC tasks with relatively small datasets. In short, we find out that the continued pre-training in domain is beneficial to TCC tasks on relatively small datasets, and overall, TAPT Lite is able to improve the model performance on TCC tasks. So above is all our study, and I would like to give some takeaways. So first, in the context of TCC tasks, BERT and RoBERTa generally perform better than XLM. Second, using a simple downstream network architecture is a better choice over a complex one such as CNN and BiLSTM. Third, TAPT Lite shows advantages to downstream TCC tasks when the dataset size of the downstream tasks is relatively small. Last, with TAPT Lite, all other variables being equal, no approach setting will sufficient to obtain the best achievable results of a model in most cases. This potentially makes the TAPT-based methods more accessible and easier to train, especially in the situation when we don't have so many computation resources. So that's all. Thank you.